7.5 Logistic Growth, How Populations Grow. In section 7.4 we showed that when the rate of change of a population is directly proportional to the size of the population grows exponentially. This seems like a reasonable model for population growth in the short term, but populations in nature cannot sustain exponential growth for very long. Available food, habitat, and living space are just a few of the constraints that will eventually impose limits on the growth of any real-world population. The logistic differential equation. Now consider the case of a population P with a growth curve as a function of time that begins increasing and concave up as an exponential growth, then turns increasing and concave down as it approaches the carrying capacity of its habitat. In other words, it starts leveling off because there's going to be a maximum amount that the habitat can support. A logistic curve like the one shown in the figure has the shape to model this growth. Let's take a look at the difference and then we'll come back to this page. So we go to the next page. Here is pure exponential growth. In other words, f of x equals e to the x. And the growth happens very quickly, and in a very short amount of time, the population will be very large. In a more reasonable fashion, this is how populations actually do grow. This is a logistic function where it has the characteristics of being exponential, but then eventually the habitat can only support so much and the population will actually level off. This is the parent logistic function. We have seen that the exponential growth at the beginning can be modeled by the differential equation. So the differential equation is k times p, and that's what we saw in the last section, for some k greater than 0. If we want the growth rate to approach 0 as p approaches the maximal carrying capacity m, we can introduce a limiting factor of m minus p. So in other words, when you have one person, the factor will be 99, so you'll be multiplying by 99. So the population will increase very quickly. But as you approach 100, you'll have 100 minus 80. Now you're only multiplying by 20, which is still seems like a lot, but it's a lot less than multiplying by 99. Then when you finally get close to the carrying capacity or the maximum amount, then you're going to be multiplying by 1 and then less than 1. So that's very small. So the rate will increase very slowly as you get towards that 100, which causes the function, the actual function, to level off once you get to that maximum capacity of, in this case, 100. This is the logistic differential equation. Before we find its general solution, let us see how much we can learn about logistic growth just by studying the differential equation itself. So here is the exponential equation. This is the logistic equation. Example 4. The growing rate of a population P of bears in a newly established wildlife preserve is modeled by this differential equation. This is the k times p times m minus p. So there's the m, there's the carrying capacity, and here's your k, where t is measured in years. A. What is the carrying capacity for bears in this wildlife preserve? Well, the m is 100. So A, we have the carrying capacity is 100 bears. And letter B says, what is the bear population when the population is growing the fastest? So we want to know when this rate is at a maximum. So we want to find the derivative. Let's find the derivative of the general equation. We're going to do d2p over dt2. We're trying to set the second derivative equal to 0. But let's find the second derivative. Now remember, the first derivative, the rate, dp over dt, is equal to kp times m minus p. Well, remember, k is a constant and m is a constant. So the only variable here is p. We have first times derivative of the second. Derivative of this constant would be 0, and then we'd have negative 1 plus the second, m minus p, times the derivative of the first, which is k. Well, we're going to set this equal to 0 because that's where mins and maxes happen. We have negative kp, then we have plus km minus kp. Let's go 0 equals, there's two of these now, so negative 2 kp, and then plus km. We're trying to get p by itself. Let's add over 2 kp, and that's equal to km. and then divide by 2k. So P equals K times M over 2k. Well, those cancel out, and as it turns out, the population is growing the fastest when the population has reached half of its maximum capacity. So the answer to letter B, you don't have to go through this whole process to answer this question. When it says, when is the rate increasing the fastest, all you got to do is take half of that number right there. So the answer to letter B is 50, but I wanted to see how you can get to that half of the maximum carrying capacity. Now, letter C says, what is the rate of change of the population when it is growing the fastest? So we want to plug 50 in for the population. So dP dt when P is 50 is equal to 0.008 times 50 and then times 50 again, because you'll have 100 minus 50. And that's equal to 20 bears per year. Example 5, tracking a moose population. In 1985 and 1987, the Michigan Department of Natural Resources airlifted 61 moose from Algonquin Park, Ontario to Marquette County in the Upper Peninsula. It was originally hoped that the population P would reach carrying capacity in about 25 years with a growth rate of the following. A, according to the model, what is the carrying capacity? Well, that's 1,000 moose. With a calculator, generate a slope field. We really don't do that. Letter C, solve the differential equation with the initial condition P of 0 equals 61 and show that it conforms to the slope field. We have dP is equal to 0.0003 P times 1,000 minus P times dt. We'll multiply the dt over. Now let's get the p's with the dP. We'll leave the constant on the right side. We have 1 over P times 1,000 minus P dP. That's equal to 0.0003 dt. We're going to have to do partial fractions on this side. We need A over P plus B over 1,000 minus P. Let's get common denominator. We need to multiply this by 1,000 minus P and this one by P. Now we have A times 1,000 minus P plus BP, and that's equal to this numerator over here, 1. Well, if we let P equal 1,000, we have, this will be 0. We have 1,000 B equals 1. B equals 1 over 1,000. When we let P equals 0, we get 1,000 A equals 1. Now A equals 1 over 1,000. This becomes the integral of, we got to take the integral of both sides, 0.00 tenths, hundredths, thousandths over P, and then plus 0.001 over 1,000 minus P. 1/1000th is the same as 0.001. dP is equal to 0.0003 dt. Let's multiply before we do the integral. We're going to multiply everybody by 1,000. We get 1 over P plus 1 over 1,000 minus P dP is equal to 0.3 dt. And we're integrating both sides. The antiderivative is the natural log of the absolute value of P minus natural log of the absolute value of 1,000 minus P, and that's equal to 0.3t plus C. Now, I have the advantage of knowing, being able to know where we're going with this, and we actually want to multiply both sides by -1. That way we have natural log of the absolute value of 1,000 minus P minus the natural log of the absolute value of P is equal to -0.3t minus C. Now we have the natural log of 1,000 minus P over P, and that's equal to -0.3t minus C. And we really don't have to worry about the absolute value because we're not going to have a population that's negative. So there's no chance of those being negative anyway. Now we have 1,000 minus P over P is equal to E to the negative 0.3 T minus C, because we're going from logarithmic to exponential. When we do common denominator on the left side, we have 1,000 over P and then minus 1. So now we can write 1 plus E to the negative 0.3 T minus C. And we've added this 1 over to the other side. Now we have 1,000 over P is equal to 1 plus e to the negative 0.3 t times e to the negative c. Now think about if you multiplied these two together, you would subtract the exponents. So we're kind of working backwards with that. Now it's time to introduce the point that we're given. We're told that p equals 61 when t is equal to 0. And this is going to allow us to find that constant. We have 1,000 over 61 is equal to 1 plus e to the 0 times e to the negative c. We have 1,000 over 61 minus 1 is equal to e to the negative c. When we take 1,000 divided by 61 minus 1, we get approximately e to the negative c is 15.393. Well, now we can go back up to, let's see, where do we want to go? How about right here? 1,000 over p is equal to 1 plus 15.393 e to the negative 0.3t. Now we can just divide by all of this and multiply by p. So p is equal to 1,000 over 1 plus 15.393 e to the negative 0.3t. Logistic growth models. The general logistic formula, the solution of the general logistic differential equation, dp over dt equals kp times m minus p is equal to, that was the 1,000 over 1 plus, this was the 15.393, then e to the negative 0.3 times t. But in this case it has m over 1 plus a, that's a constant, e to the negative mkt. Where a is a constant determined by appropriate initial condition, the carrying capacity m and the growth constant k are positive constants. In exercises 23 to 26, a logistic equation describes the growth of a population P, where T is measured in years. In each case, find A, the carrying capacity of the population, B, the size of the population when it's growing the fastest, and C, the rate at which the population is growing when it is growing the fastest. Letter A, the answer is 700. Letter B, the answer is half of that, 350. And letter C, they want to know dP over dt is equal to 0.0008 times 350 times 350 again, because you're going to have 700 minus 350. Solve the initial value problem using partial fractions. Use a graphing utility to generate a slope field for the differential equation. Verify that the solution conforms to the slope field. 28, we're going to solve the differential equation. We have dP is equal to 0.0008 p times 700 minus p dt. Let's get the p's with the dp. We have 1 over p times 700 minus p. dP is equal to 0.0008 dt. Now we're going to integrate both sides to solve the differential equation. We're going to use partial fractions for this. We have a over p plus b over 700 minus p. We'll have a times 700 minus p plus b times p, and that's equal to 1. That's equal to the numerator of that right there. We'll let p equal 700. We'll have 700b equals 1, b equals 1 over 700. We will let p equals 0, and that will give us 700. A equals 1, so A is also 1 over 700. That gives us 1 over 700 p integral plus 1 over 700 times 700 minus p is equal to the integral of 0.0008 dt. Let's multiply everybody by 700. We'll have the integral of 1 over p plus 1 over 700 minus p dp, forgot the dp over here, is equal to the integral of 0.56 dt. We'll have natural log of the absolute value of p plus, actually not plus, it's a tricky little minus there. We'll have minus natural log of the absolute value of 700 minus p, and that's equal to 0.56 t plus c. Well, we actually want the 700 minus p on top. We're going to multiply by -1 natural log of 700 minus p minus natural log of p. That's equal to -0.56 t minus c. Now we have natural log of 700 minus p over p is equal to -0.56 t minus c. Let's go from natural log to exponential. We have 700 minus p over p is equal to e to the -0.56 t minus c. 700 over p is equal to 1 plus e to the -0.56 t, and then we have times e to the -c. And here's where we introduce the point that we were given, and that is p equals 10 when t equals 0. P equals 10 when t equals 0. We have 70 is equal to 1 plus e to the 0 is going to be 1, and then we'll have plus e to the -c. We have 69 is equal to e to the -c. 700 over p is equal to 1 plus e to the -0.56 t, and I guess we could put the 69 out front. It's usually the coefficient of e. P now is equal to 700 over 1 plus 69 e to the -0.56 t.